Hi, good afternoon, everyone. My name is John Chan, and I'm from Bryan Research and Engineering. Welcome to the Flares and Emissions webinar. A little bit of introduction about myself. I graduated from Brigham Young University in the US with a bachelor's in chemical engineering. And I've been working with Bryan Research and Engineering for about 7 years right now. And my role in the company is technical support. And joining me in this webinar are my colleagues. They are Joachim, Ganang, Dee, and Omar. Okay, let's discuss a little bit about the agenda today. We will be discussing about the purpose of the flare and some of the common pollutants. And we'll then go into the setup in ProMax, how we model in ProMax using incinerator model and also a flare. In this webinar, flares and incinerators, they're both modeled in the same way in ProMax. Incinerators or thermal oxidizers, they are slightly different from flares. The similarity is that they both use combustion to dispose of the natural gas. The difference is in flaring. The gases are usually piped to a remote and elevated area, and they are burned in an open flame and open air. Okay, and flares they also usually use a specially designed burner tip. However, in the incinerator, the combustion usually happens below or within the stack. Okay, and as far as I know, the government and industry, they usually do not differentiate between flaring and incinerators. Both are in the so-called flaring category. And after that, we'll then move on to two case studies. And one case study is matching the plant operating data. And another case study is we'll be discussing about the low NOx burner. Why do we flare? Okay, flares they are actually common in petroleum refineries, gas plants, chemical plants, production facilities, and most of you have probably seen them some point in your life. They look like a candle flame on top of a tall chimney. Flaring is a important safety device during operations and gas facilities. It can happen during startup or shutdown plant or when there is a loss of power. And this is done to prevent the gas from accumulating in the equipment and thus creating a potential hazard. Other times, the reason may be due to simple economics. Okay, for example, at production facilities, less valuable gas may come along with the crude that is being extracted, and producers must therefore somehow think of what they want to do with the gas, so that they don't have to stop pumping the oil. And they have to think about questions such as, is it worthwhile to invest in additional pipelines and processing facilities for the gas? What is my capex and what is my opex? And is it profitable to build and process the gas in the long run? If the answer is no, they would usually vent the gas, or they would actually flare it. Okay, venting the gas is actually releasing it directly into the atmosphere. Flaring is usually the preferred method, and that's mainly because methane is a greenhouse gas, and it produces carbon dioxide when burned, and which contributes to the carbon footprint. If you are aware, methane has a much higher global warming potential than carbon dioxide. Okay, so most of the time the gases are flat. And lastly, toxic gases such as your H2S needs to be incinerated. They can't just be simply released into the environment. And what this does is that it converts your harmful H2S into less toxic compounds. However, if your H2S is present in significant amounts, in very high amounts, usually SRU is needed to process and convert the H2S into elemental sulfur, and the remaining H2S in the tail gas will then be sent to the incinerator. I thought it would be helpful to discuss some of the common classifications or types of air emissions at the beginning. Some of you may have heard of these acronyms actually. So the first one I want to discuss is hazardous air pollutants. They are actually a chemical specifically designated by the EPA in the US as having adverse human health or ecological impacts. Okay. The original list, I believe, contains almost about 200 pollutants, and this includes your compounds such as your BTEX, methanol, chlorine, etc. Next is your volatile organic compounds, or VOCs. Okay, they are actually defined as any carbon compound which participates in the atmospheric photochemical reactions. Basically, they are your C3s and above. Methane and ethane, they are not included. And excluded from the list are also your carbon dioxide and carbon monoxide, things like that. As mentioned earlier, your BTEX, which is your benzene, toluene, ectobenzene, and xylenes, they are actually classified under your hazardous air pollutants. And because they are also carbon-containing aromatic compounds, they are also classified under VOCs as well. And these compounds, they make up considerable fraction of the hydrocarbon that is being produced from your oil and gas wells. And they are thus of concern to operating companies and environmental regulators like the EPA. Okay, so we need to take note of your BTEX emissions as well. Next is your greenhouse gases. Okay, most of you are probably familiar with this. Lots of debate recently about how greenhouse gases contributes to climate change. Carbon dioxide is the most common one, and they are released from both process and combustion sources. Other common greenhouse gases includes your methane and your nitrous oxide. Okay, last of all is your nitrous oxides, your NOx, and your sulfur oxides, your SOx. Okay, NOx, they are your nitrogen dioxides, your NO, and your N2O. They of this group, nitrogen dioxide is probably generates the highest interest and is thus tracked as an indicator for the larger group of your NOx. Okay, they are typically formed during high temperature combustion. Okay, for your SOx, they also needs to be tracked as well because they are toxic gas. Okay, both your NOx and SOx, they can contribute to acid rain when they are reacted in the atmosphere. Okay, in ProMax, there is a way for you to calculate the air emissions. For those who are familiar with ProMax, we have a tool which is called the air emissions stencil. And what this tool does is that it actually allows the users to display these emissions in ProMax on your flow sheet. Okay, and the stencil is actually located on the ProMax ships on the left. Okay, if you are unable to find the stencil, you can contact us. Okay, and we'll send you the stencil. And in this list, you can also see that there is a GWP calculator somewhere in the middle. And what this calculator does is that it actually calculates the mass equivalent of CO2 that is generated from a particular stream. Once you drag out this stencil, you can drag out this block called the sum components. So this is located on the right-hand side. And once you drag it out onto your flow sheet, you can then select which process stream you want to report the emissions and what basis, whether you want it to be in mass flow rate, molar flow rates, and also the units that you want to report it. And underneath, you can then select the components that you want to report. So you can customize if you want to have your BTEX, your greenhouse gases, things like your NOx and your SOx to be displayed onto your flow sheet. So once you have selected those groups, ProMax will display this onto your flow sheet. Okay, we'll do a demonstration later. Okay, let's move on to discuss a little bit about the setup of the incinerator or the thermal oxidizer. Okay, they are these terms they are used interchangeably. The thermal oxidizer is very basic in design. It consists of a burner and a combustion chamber. You can see on the picture on the right. And its purpose is to convert the combustible components, such as your VOCs, to less harmful species through the use of heat. Okay, so in this example, we have your propane, and it is being oxidized to form your carbon dioxide and your water. So we have the air to provide the source for oxygen. A complete combustion will yield water and carbon dioxide. There shouldn't be a shortage of oxygen such that a reasonable flame temperature cannot be maintained. Okay, for most incinerators, typically we want to maintain a stable flame temperature of around 1600 Fahrenheit, and that's about 870 degrees Celsius. Higher than that would require a more expensive refractory to avoid heat damage. And you may ask, why are we so concerned about this combustion temperature? Well, the reason is because we actually want to ensure that we maintain a stable flame temperature, because this outlet temperature is actually one of the primary indicator of the performance of the incinerator. And it actually tells you if the combustion is happening efficiently. As mentioned earlier, proper combustion requires high temperature. So if the amount of combustible material in the stream itself is insufficient to reach an adequate temperature, you will need to add fuel gas to increase the heating value. And for flares, typically you want to increase the heating value to at least 2 to 300. That's the lower limit, 2 to 300 BTU per cubic feet. Combustion or destruction removal efficiencies, they are usually 98% or greater if your incinerators are properly designed and operated. The EPA actually allows companies to assume a 98% destruction of the chemical species if the manufacturer efficiency is not available. Incineration can yield a number of different species. The exact quantity and relative amount of each depends on your feed composition and also your combustion temperature. As mentioned earlier, the complete combustion of your carbon species will yield CO2 and H2O. However, if the combustion is not complete, such as if your oxygen is insufficient, then carbon monoxide and H2, your hydrogen may form as well. So you may need to take note of that. If sulfur species are present in your feed, such as your H2S, then products such as your SOx may form. And similarly, if you have nitrogen species present in your feed, such as your ammonia, then NOx products will form. When modeling these reactors in ProMax, there are actually a few different ways where we can actually handle the different reactions we expect to see. One of the ways is through the Gibbs minimization method. And this method is really the simplest method when we want to simulate flares and incinerators in ProMax. And what do I mean by that? The Gibbs minimization method actually allows the user to ignore the kinetics and the reaction path. And this means that the stoichiometric equations are not required from the user. Instead, what we do is that we take the known reactants and we tell ProMax what possible products could form, and we allow ProMax to minimize the Gibbs free energy of our reactants and products, which basically will be our equilibrium point at the end of all our possible reactions. So basically, we have made things very simple for the user, and that's the advantage of Gibbs minimization. And as soon as I choose the type of reactor, ProMax will then ask me to choose a Gibbs set. And these Gibbs set are just pre-configured reactors for common applications for this Gibbs minimization method. So if you can look at the figure on the slide, if you look at the drop down, you can see that there are some reactors for your SRU that is being set up. Okay, things like your sulfur condensers and Klaus beds. And when you model an incinerator in ProMax, you would use the Gibbs minimization type with the burner Gibbs set. And one thing to keep in mind when using the Gibbs minimization reactor type, okay, is that you would need to make sure that any expected reaction products are included in the project environment. So you not only need to add your reactants, but also your products such as your CO2, your water, your carbon monoxide, this kind of products. Continuing down on the screenshot, you'll notice that there is a bypass fraction as well. And what this bypass fraction does is that it actually represents how much of our reactants go through the reactor without reacting. Okay. And this means that if I specify a 2% bypass fraction, that will be the same as 98% equilibrium conversion or combustion efficiency. Okay, let's take a look at the ProMax model. So let's take a look at the ProMax shapes. Okay, so in ProMax, when you want to model an incinerator or thermal oxidizer, you need to select the shapes from the ProMax reactors. So we have these blocks, and what I did was I drag out this block incinerator and I drag it out onto the flow sheet. So we have this incinerator here. Okay, we have the waste gas stream. In this case, we have the tail gas, and this tail gas actually coming from your sulfur recovery unit. It can also be an acid gas that is coming from your amine regenerator. Okay, let's take a look at the composition of this tail gas. So you can see that in this tail gas, the composition, mostly we have our carbon dioxide, okay, we have our nitrogen, we have some hydrogen sulfide, which we need to combust to turn it into our salts. Okay, so you can see that the majority of this stream are inerts. Okay, so there's not a lot of combustibles in this stream. And if you take a look at the net ideal gas heating value under this property tab, you can see that the heating value of this stream is quite low. Okay, so most likely we would need to add in fuel gas to increase the heating value. Let's also take a look at the environment. Okay, so under the ProMax menu, I'll select the active environment. So the property package that I am using here is Ping Robinson. Okay, you can also use sulfur. Okay, you can also use sulfur PR or sulfur SRK. Under components, you can see that I have listed not only my reactants, okay, but I've also added the products, which are my sulfur dioxide, my carbon monoxide, and hydrogen. okay, and water. So you need to make sure these components are added into your environment. Let's set the fuel gas here. Okay, let's set it as zero flow first. And I'm going to solve this block. Okay. So what basically this combined gas stream is equivalent to your tail gas. Okay. And in order to combust this, your hydrogen sulfide, you will need oxygen. And how do I know how much oxygen I would need? You can actually find the amount of oxygen that's needed for combustion by clicking into this stream. And on the tab here, Analysis, we can click on the Add Analysis tab. And once you click on this Add Analysis tab, okay, we have this window that shows up. Okay. If you click on the Combustion Analysis, okay, you can see that on the first property, it shows you a property called Required Combustion Oxygen. Okay, and if I click on Solve, I can see that ProMax is actually telling me that I would need about 2.375 kilomole of oxygen in order to completely combust our H2S. So now that I know how much oxygen I would need, I would go into my airstream. Okay, I have my temperature and pressure defined here, but I will need to also set up how much I will need to feed into the burner. One way that we can do that is we can actually manually define or input our oxygen flow rates into the tab here under composition. Okay, so we can actually put in the molar flow rate and put in our oxygen flow rates. But I do not want that, because what if I also have to think about if my feed flow changes, or if I need to add in my fuel gas, then my required oxygen for combustion would change as well. So I will need to manually go back to this stream and adjust my oxygen flow rates. And that's going to be a hassle if my flow and my composition of my combustibles keep changing. ProMax can actually simplify this for me. And what I'm going to do is I'm going to add a simple specifier. And what this simple specifier does is that it calculates one variable that is dependent on another variable. In this situation, my airflow rate is dependent on my required combustion oxygen. And in order to create a simple specifier, I would go into this air stream. I would right click on to the flow rate. Okay. And I would select Create Simple Specifier. I can change the name of my specifier here. I'm going to change it to I'm going to rename it to Airflow Specifier. And in this box here, this is where I would write my governing equation or expression in this box. Okay. I'm not going to go into too much detail of how we write this expression, but what I'm going to write is that I need to write my required oxygen. So I'll need my required oxygen property, which is that 2.7 kilomoles of oxygen, and I will need to divide it by the mole fraction of my oxygen. Okay, so I will divide by my mole fraction of my oxygen, and that's because this is an airflow rate stream. This is not a purely an oxygen stream. Okay. And what I will do is I will also need to add in excess oxygen. So let's add in about 20% excess oxygen. So what I will do is I will multiply it by 1.2. Now ProMax doesn't really know what my required oxygen and XO2 means. Okay, so I'm gonna tell ProMax what these two variables are. And to do that, I will come to this add button, and that will bring up this window, which is our moniker tree. Okay, so this would allow me to find that property. So I'm gonna open this up. I'll go to my flow sheets, okay, incinerator, and go to P streams, combined gas analysis, combustion analysis, properties, and I will select my required combustion oxygen. And you know that you have selected the correct moniker if you see that a moniker shows up here. Okay, this is like an address to the property. And now I will name this property or this variable. I'll need to rename it exactly the same as what I wrote on the expression. And once I do that, I'll click on Add. Okay. Next, I'll need to add my mole fraction of my oxygen in my airstream. Okay, so to do that, I'll click on Add again. And this time I'll go to my airstream, go to Phases, Total, Composition, and I'll select mole fraction, oxygen. Okay. I'm going to change my units to fractional. So you can see that now I have set up my specifier to feed in 20% excess oxygen into the burner. So now when I've done that, you can see that the streams have turned maroon. Okay. Now I'll need to set up my incinerator. Okay, so to do that, I'll double click into my incinerator here. I'll go to my process data tab. So first of all, I'll need to change my type to Gibbs minimization. And once I have selected Gibbs minimization, I would then select the Gibbs set, which is burner. Once I've selected this two, okay, I'll need to adjust my, I'll need to define my pressure drop. Let's give a pressure drop of 0. Okay. And down below, you can see that there is a bypass fraction. Let's assume that the bypass fraction is 2%. So what we're doing is we are assuming that this is a 98% efficient combustor. So once I have everything defined, I can go ahead and solve my flow sheet. Once you have solved your flow sheet, you can see that your streams and your objects should turn green. Okay. I have my message box open up below here. If you can see what is written on the message box, okay, it actually gives you a warning. Okay, it says that for reactor incinerator, okay, the adiabatic flame temperature of about 400 degrees Celsius is below this temperature, which is recommended to maintain a stable flame. Okay, so what this means is that my outlet temperature here is too low, so it is unable to maintain a stable flame. So what I'm gonna do is I will need to add in my fuel gas to get my temperature at my outlet to at least 1600 Fahrenheit or about 870 degrees Celsius. So I'm gonna close this. So I'll go into my fuel gas stream. Okay. Right now, I have my molar flow rate set as 0, but I want my outlet temperature to be at least 870 degrees Celsius. Okay, and what I would want to do is I will want to adjust my fuel gas so that I will get an outlet temperature, a desired outlet temperature. Okay, and what I can do here is I can actually create a simple solver. Okay. What a simple solver does is that they're actually used to manipulate one variable in order to achieve a target in another. Okay, and generally it will require a few iterations to find the value that you're looking for. Okay, so what I will do is I will right click on this molar flow rate and I will create a simple solver. Okay. So you can see that we have this box here. Okay, and what you want to do is you will want to write your equation such that it is equals to 0. So one way that I can write it is I can write it as outlet T minus 870. Okay, there are other ways to write it, but this is how I'm going to write it here. And again, I need to tell ProMax what my outlet T is. So I need to click on Add. Okay, I'll go to my outlet stream, phases, total, properties, temperature. Okay, I'm going to rename it as outlet T and select Add. Next, once I have defined my or I've written my expression, I will need to tell ProMax or give it an initial value for it to start the iteration. So I'm gonna give it an initial value of say 10 kilomoles first. Okay. So once you have done that, you can just close, and I'm gonna re-execute this flow sheet. So after a few iterations, you should be able to see that ProMax has calculated a required fuel gas flow rate to get a desired outlet temperature. Okay, so right here it requires about 2.6 kilomoles of your fuel. I have a cloud here that actually reports how much of my sulfur dioxide is being emitted into the atmosphere. Okay, and as discussed earlier, okay, we can actually also use another stencil, which is called the air emission stencil. So this can be found under more shapes. Okay, and you can then click on ProMax air emission stencil. Okay. Once you see this, you can drag out this shape, which is called the sum components. I'm going to drag it onto my flow sheet. Once you have dragged it out, it will ask you which stream you're interested in. I'm going to select my outlet stream. Click OK. And you will then create a window here that actually allows you to customize which of the components you want to report. So you can report your BTEX, your greenhouse gases, your SOx, and your NOxes. Okay. So if you have an atmospheric tank, and if let's say you have a pressurized liquid, feeding into the atmospheric tank, you will expect some flashing losses. So you can actually report those emissions on using this sum components stencil. I'm going to also show you a flare example. What we have here is that we have a flare. Okay, and it is being set up and is calculated for us, is solved. Okay. And what I want to demonstrate here is that this feed gas, it actually goes through your amine unit and your dehydration unit, and after those processing units, it actually goes to the flare. The flare here if you take a look at the flare, the composition, okay, you can see that we have a small amount of your hydrogen sulfide, okay, and we also have some hydrocarbons, okay, your methane, your ethane, propane, and also your BTEX, okay. So BTEX can actually be present in natural gas streams, and they can actually be picked up in glycol dehydration and amine sweetening units. Benzene is actually a known carcinogen, and your BTEX can actually cause adverse health effects to humans. So they just can't be simply released into the atmosphere. Okay. And in this flare example, you can see that in this stream we actually have enough hydrocarbons that would burn without adding fuel gas. If you look at the net ideal gas heating value here, okay, so this net ideal gas heating value is actually quite high compared to what we saw earlier from the incinerator example. Okay, and as I mentioned, for flares, we will expect at least a heating value of at least 300 BTU per cubic feet for air and steam assisted flares. However, efficient combustion of all the species, they actually might require a higher heating value than this minimum. Okay, and so you can see that for the treated gas, we actually do not need to send in any fuel gas into the flare. And another point that I want to point out is the amount of oxygen that we are feeding into the flare here. If I go to the molar flow, you can see that I also have a simple specifier that is being set up. Okay, if I go to this simple specifier, you can see that the excess oxygen that is being fed is 180%. So this is actually much higher than the 20% that we saw in the example just now. And the reason why we feed in so much excess air is that it actually controls the outlet temperature of this flare so that it does not go too high of a temperature. Usually, a convention to use is to feed in about 170% excess oxygen to fully combust all the species in your feed. So this flow rate of the air is actually largely determines the temperature of the outlet of the incinerator. The excess air, the purpose is to drop the outlet temperature so that there is actually more mass to absorb the heat. From a cost standpoint, the amount of air in excess of the stoichiometric amounts should actually be minimized. But it also has to be sufficient enough to absorb the heat such that the metal skin does not exceed a certain temperature limit. So typically we do not want the temperature here to go too high. Typically we would see about 18 to the highest amount that I've seen is about 18 to 2000 Fahrenheit, or 1800 to 2000 Fahrenheit, and that's approximately about 1000 degrees Celsius. So that's the example that I want to show you, and this flare, it is actually configured the same way as the incinerator example that I previously showed you. So in the process data tab, you can see that the type here it is also set up as Gibbs minimization reactor, and the Gibbs set is defined as the burner Gibbs set. So you can see that the amount of BTEX in stream number 1, okay, is about 20 tons per year. Okay, and once we incinerated the waste gas stream or the combustibles in in the waste in the feed. Okay, you can see that the amount of BTEX actually reduced to about 0.4 tons per year. And because we have also some hydrogen sulfide, okay, as well, we also would be forming your SO2. So those also need to be included in the environment. So you can see that we have some amounts of SO2 that is being formed. Now I'm going to discuss two case studies. The first case study is actually from one of the operators in Asia. I also want to bring up this case study because some of you may wonder, is using Gibbs minimization reactors really reliable, and are they really accurate? So that's why I want to bring up this case study. So this operator actually sought our help to match their acid gas incinerator. They want to match their acid gas incinerator operating results in ProMax, and they were trying to use the model to perform some sensitivity analysis. I have sought their permission, and they have actually agreed to show you this model in this webinar. So let's take a look at this model. You can see that I have set up this model here. So this is an acid gas incinerator. So this is actually an incinerator in an LNG facility. And what they have is that they have this acid gas that is coming off from the acid gas unit, or the amine regenerator. And let's take a look at the composition of this acid gas. So you can see that in this acid gas, we also do not have too much of my combustibles. Okay, we have a lot of CO2, okay, a little bit of very tiny amounts of your hydrocarbons, and we also have some H2S as well. And in their acid gas incinerator, they have a temperature indicator at their incinerator stack, okay, that actually feedback to the fuel and to the airflow controller, and that is to avoid sub-stoichiometric combustion. So they want to ensure that they actually feed in excess oxygen into the incinerator. They also have an oxygen analyzer, okay, at the outlet of the combustion chamber. So you can see that they have reported these two values. So they have these two values at their DCS, and they also know what their feed composition is, okay, their fuel gas, and also their airflow. So what I did was I plugged in those numbers, okay, into the inlet. And what I did was I used the Gibbs minimization type reactor, and I used the Gibbs set. I used the burner as my Gibbs set. And you can see that once I put those in, you can see that ProMax actually matches quite well to the actual plant data. So you can see that the difference is not too big. The one in red are those that are reported from DCS. All right, so let's take a look at another case study. So this case study is actually also from another operating company. So this operating company is actually also located in Asia. They have an existing incinerator, but due to changes in government regulations, a more stringent requirement for the NOx emissions is required. So they can't emit as much NOx as before. So this waste stream is actually coming from a two-stage saltwater stripper in a refinery, specifically the overhead of the ammonia stripper, which means that this waste stream has a very high concentration of ammonia. And we know that when oxidized in a single stage thermal oxidizer or incinerator, very high amounts of NOx will be produced, which will exceed the NOx emission limit. So what they did is they actually went to incinerator manufacturer to get additional details of possible methods to reduce the NOx emissions. And what the manufacturer came back is that they actually proposed a multi-stage thermal oxidizer, or what we call a low NOx burner. And this operating company actually asked us to model this such that they can actually perform some feasibility studies. So let's take a look at how this is set up. So this is a simple diagram of a low NOx burner or a multi-stage thermal oxidizer. So this thermal oxidizer treats the waste gas stream in a 3-stage process that actually provides a near complete oxidation of both the organic and nitrogen compounds at the same time, while minimizing the emission of your NOx. The waste gas stream is first subjected to temperatures of around 200 Fahrenheit, while minimizing contact with oxygen that is found in the combustion air. And this occurs in the stage 1 of the process. At this elevated temperature, combined with substoichiometric oxygen concentrations, it actually creates an environment where the formation of molecular nitrogen actually occurs more readily than the formation of nitrogen oxides, your NOx. So what this means is that the ammonia that is in the feed will actually decompose to form molecular nitrogen rather than NOx. And because this is a highly exothermic reaction, steam or water will then need to be injected to prevent the operating temperature in stage 1 from escalating above the desired set point. So that is the stage 1. So it's slightly different from what we saw earlier. We do not feed in excess oxygen. We feed in substoichiometric oxygen. So in stage 2, what it is actually happening in stage 2 is that the flue gas that is coming off from stage 1 is then cooled by injecting water. So we inject water to maintain a flue gas temperature of between 13 to 1600 Fahrenheit. And finally, at the last stage, excess air, okay, is then injected into the flue gas stream in stage 3 to complete the combustion process. So this is used to achieve the mean flue gas temperature below a certain temperature, so that the temperature doesn't go too high. And the flue gas is then discharged into the atmosphere via the vent stack. So let's take a look at how the model is being set up here. So this is a setup of the low NOx 3-stage thermal oxidizer. So let's take a look at the composition in the waste gas or in the feed. Okay. So you can see that in this waste gas we have about 96% ammonia. So that is a very, very high amount of ammonia that is in your feed. So it's not feasible to send this to a typical incinerator or a direct stage thermal oxidizer. So we actually need to send this to a low NOx 3-stage thermal oxidizer. Okay. So what we have here in our airstream, okay, if I go to my airstream and I double click onto the flow rate, okay, so what we did is we feed in a substoichiometric amount of oxygen. So we feed in about, you can see that the value that we type in here is 0.7. Okay, so we feed in about 30% less oxygen than what is required, and you can see this in the required in the cloud here. Okay, so in the waste gas, I have actually created a analysis on what is the required combustion oxygen. So the required to fully combust our ammonia and H2S is about 75 kilomole. And in our air, you can see that we feed in only about 53 kilomole of oxygen. Okay. And we also have this steam cooling injection stream. This is actually basically you can feed in your water or your stream. In this case, it is water. Okay. And what we did here is that we actually created a simple solver on our flow rates of our water to actually achieve 200 degree at the outlet of stage 1. So ProMax is actually adjusting how much water to feed into the burner, such that the temperature is 200 degrees, 2000 degrees Fahrenheit. Okay, so you can see that in stream number 3, ProMax has actually calculated how much of my steam that is required to get to my desired temperature of stage 1. So the outlet of my flue gas in stage 1 is then sent to stage 2. Okay, and what we are doing here is we are injecting more water to control the temperature in stage 2 to around 1300 to 1600 Fahrenheit. Okay, so similarly, we actually created a simple solver, okay, to control my water flow to achieve a desired temperature at the outlet. By the way, the text in red fonts, they are actually provided by the manufacturer or the vendor, and this is what they actually provided, or these actually estimated values that they would expect to see for the feed composition that is in the waste gas. In stage 3, what we did here is that we actually are feeding in excess oxygen. So you can see that the required combustion oxygen in stream number 8 is about 28 kilomoles, and we are feeding in about 33 kilomoles of oxygen. So again, we have a simple solver on our airflow rate. Okay, you can see that I've set up a solver here to get my outlet temperature to around 980 degrees Celsius, okay, which is what they would expect to see. Okay, so you can see that once we have set this up, and by the way, all these reactors, they are set up as Gibbs minimization reactors. So if I go to the reactors here, you can see that the type, okay, again, Gibbs minimization, and I'm using the burner as the Gibbs set. Okay, so all these are all using Gibbs minimization reactors. Okay. And you can see that for under here, okay, so this is what the vendor estimates what the emission at the outlet would be. Okay, so it predicts how much of your CO2 will be emitted, how much of your SOx will be emitted, how much of your NOx is emitted. Okay, so you can see that in ProMax, we actually measures quite well to what the vendor expects to see. And what I really want to, I guess, point out here is that you can actually use the Gibbs minimization reactor to model your incinerator and your flare, and you can actually trust ProMax to give you accurate results when modeling these flares and emissions. Thank you all for coming. This is the end of the webinar. If you have any questions, you can feel free to reach out to any one of us for support or questions. And you can also write into support@bre.com, and we'll be there to help you out.